And now since we have studied limits both formally and informally, and we know that this limit x tends to a fx is equal to L if value of fx it approaches L when x approaches a. Now we have already studied that this x can approach a from two sides, either from the left hand side or from the right hand side. If x approaches a from the left hand side, we know it is x tends to a negative, and from the right hand side it is x tends to a positive. So depending on whether we are approaching this function from the left or from the right, we have defined something called as one-sided limits. Now in one-sided limits we have left-hand limit, and in this left-hand limit we approach this function from the left-hand side. So we'll simply write limit x tends to a negative fx, and if we approach this function from right-hand side, then we'll say it is right-hand limit. So we are going to write this right-hand limit as limit x tends to a positive fx. So in the first case, we are approaching this function towards a from the left-hand side, and this is your left-hand limit, and in short we call it LHL. And if we approach this function towards a from right-hand side, we call it right-hand limit, or simply RHL. So these are called as one-sided limits. Say for example, I'm given this limit, say this limit x tends to 0 e to the power minus 1 upon mod x plus 1 by x. Now if we want to write its left hand limit, it will be simply this limit x tends to 0 negative e to the power minus 1 upon mod x plus 1 by x. So here we are approaching this 0 from the left hand side, and if we approach this limit from the right, we say it is right hand limit, and we are going to write this as limit x tends to 0 positive e to the power minus 1 upon mod x plus 1 by x. So in this case, on the left hand limit, we are approaching 0 from the left hand side, that is through negative numbers, and for this right hand limit, we are approaching 0 through right hand side or through positive numbers. Now when we are approaching 0 through left hand side, then we know all these numbers in the neighborhood of 0, they'll be negative, and if x is less than 0, we know that mod x is minus x. So if we put mod x as minus x, we'll write this as limit x tends to 0 negative e to the power minus, and this is 1 upon minus x plus 1 by x, which will cancel, and this is e to the power 0, and e to the power 0 is 1. And if we approach this limit to the right when x tends to 0 positive, now in this region when x is greater than 0, mod x is simply x. So this is limit x tends to 0 positive, and this is e to the power minus, and this is 1 upon x plus 1 upon x, and it will be this limit x tends to 0 positive e to the power minus 2 upon x. Now if we use direct substitution to find its form, this is e to the power minus infinite. In the previous section we have studied a to the power minus infinite is 0 if a is greater than 1. Now value of e is 2.7 something, so this is greater than 1, so value of this right hand limit is 0. Now in this example, if we look at this limit, then we find that if we approach this limit from the left, we get value 1, and if we approach it from the right, we get this value 0. So we are getting two different values when we approach it from two different directions. So in this case, if we approach this function from the left, we reach 1, and if we approach it from the right, then we reach 0. So in this case, we have different values for left hand limit and right hand limit. So this is how left hand limit and right hand limit, one-sided limits are defined. Now we'll consider some cases when limit does not exist. Now a limit does not exist. Limit x tends to a fx. It does not exist if, now in this first case, when we have two different one-sided limits, when left hand limit is not equal to right hand limit. So if we have this limit x tends to a fx and we get different values for left hand limit and right hand limit, in that case this limit x tends to a fx, it does not exist, as is the case in our previous example. In this case, left hand limit is 1 and right hand limit is 0. So for this one, we'll simply say this limit x tends to 0 e to the power minus 1 upon mod x plus 1 upon x does not exist. Now the second case when this limit x tends to a fx will not exist is when we get multiple values of limit. So limit of function, it must be unique. If we get more than one value of any limit, then that limit does not exist. This is often the case when we have oscillatory limit. Say for example, if we are going to write this limit x tends to 0 cos 1 by x. Now this is cos infinite and cos infinite is oscillating value between minus 1 and plus 1. So we'll take all the values between minus 1 and plus 1, and since a limit has to be distinctly defined, it cannot take more than one value. So in this case also, limit does not exist. So value of limit, it must be unique, and it doesn't matter even if the value is infinite. Infinity is an acceptable answer in case of limits. Say for example, if we have this limit x tends to 0 1 upon x square. Now we put x as 0, it will be 1 upon 0, and 1 upon 0 is plus infinite. Now this value, it is uniquely defined, so this limit, it exists and its value is plus infinite. And if we look at graph of 1 upon x square, then from the left hand side and also from the right hand side, if we move towards 0, both these left hand limit and right hand limit, they approach positive infinity. So in this case, this limit is defined. Limit is defined and it is equal to plus infinity. So we don't have a problem with finite or infinite values. It should just be left hand limit must be equal to right hand limit, and also there should be one distinct value of this limit, whether finite or infinite. Now there will be some cases in one-sided limits where the function may not be defined in the neighborhood. Say for example, if we want to write this limit x tends to 1 positive cos inverse under root x upon 1 minus x. Now when we say x tends to 1 positive, it means x is greater than 1, and if x is greater than 1, then this cos inverse under root x, it is not defined. And when this function is not defined, so this right hand limit is also not defined. Now we take another example. Say for example, this limit x tends to 0 positive sine greatest integer function of x upon greatest integer function of x. Now this denominator is greatest integer function of x. So this function is not defined whenever greater function of x is 0. So greater function of x, it should not be 0. Now greater function of x is 0 when x lies between 0 and 1. So x, it should not lie between included 0 and not included 1. So that means in this right neighborhood of 0, this limit sine greater function of x upon greater function of x, it is not defined. So here also this limit is not defined. So whenever we have these cases when one of the one-sided limit is not defined, and if we are given this limit, say this first limit, this limit x tends to 1 cos inverse under root x upon 1 minus x. Here we are not going to check its right limit. Here we'll just check its left hand limit, and there'll be this limit x tends to 1 negative cos inverse under root x upon 1 minus x. In the same way, we have this limit x tends to 0 sine greatest function of x upon greater function of x. And since it is not defined on the right hand side, we'll consider this limit as this left hand limit only. So it will be this limit x tends to 0 negative sine greatest function of x upon greatest function of x. Now in this first case, since left hand limit is defined and right hand limit is not defined, some of the books, they say since left hand limit and right limit, they are not equal, this limit does not exist. And here also they'll say RHL does not exist, this limit does not exist. But that's not the correct way of approaching this problem. So if we are given these limits, then we'll not even talk about this right hand limit. The value of this limit will be equal to value of its left hand limit. And in this case also, value of this limit will be equal to value of its left hand limit. So if one of the side of limit is not defined, then we'll take this limit only for the side where it is defined. Now we'll study some theorems on limit. Now if we have two limits, this limit x tends to a fx, which is equal to L1, and this limit x tends to a gx, which is n, then this first result is this limit x tends to a fx plus minus gx, it will be equal to L1 plus minus L2. In the same way, if we have this limit x tends to a fx into gx, this limit will be equal to L1 into L2. Third one is this limit x tends to a fx upon gx, it will be equal to L1 upon L2 if L2 is unequal to 0. Fourth one is limit x tends to a fx to the power gx, it will be equal to L1 to the power L2 if L1 to the power L2 is a real number. Now this fifth one is very important and it is related to composite functions. Now suppose we have this limit x tends to a f of gx. Now if we have this condition that fx is continuous in the neighborhood of this limit x tends to a gx, then we can write this limit, say L, as f, and then this limit x tends to a gx. So we can take this limit inside this function f if and only if this function f is continuous in the neighborhood of this limit x tends to a gx. Now say for example, suppose we have this limit x tends to 0 negative e to the power mod x upon x. Now we know that exponential function, it is throughout continuous. So we can take this limit inside this function. So we can write this as e to the power, this limit x tends to 0 negative mod x upon x. And when x approaches 0 from the left, that means x is a negative number. And if x is a negative number, then mod x is simply minus x. So it will be this e to the power limit x tends to 0 negative. And here we'll get minus x upon x, which is e to the power minus 1. So the value of this left limit at 0 will be e to the power minus 1. So we can take this limit inside this function if and only if this function fx is continuous in the neighborhood of this limit of other function, which is limit of x tends to a gx. Now we'll discuss the methods to solve a limit. Now first method to solve a limit is simply direct substitution. This direct substitution method, it works for some elementary problems where we do not have an indeterminate form or where function definition does not break. Say for example, suppose we have to find this limit x tends to 2 x square plus x minus 2 upon x minus 3. Now as I have told you previously, the first step in any limit would be to find its form. So if we directly substitute this value, we'll get this as 4 plus 2 minus 2 upon 2 minus 3, and this value is minus 4. Now since minus 4 is not an indeterminate form, answer to this limit is minus 4. Or if we consider this case, which is limit x tends to pi by 2 sine x upon x. Now sine pi by 2 is 1 and x is pi by 2. So value of this limit is 2 upon pi, or we can write this limit x tends to 0 x sine 1 by x. Now this is 0 and this is sine infinite. Now sine infinite, it's an oscillating value between minus 1 plus 1, and 0 into anything finite is 0. So value of this limit is 0. So there will be a lot of questions where by direct substitution we can find out the value of limit. So if we do not get an indeterminate form and if the function definition does not change at the point of limit, then whatever answer we get from direct substitution is our answer. Now these are very simple and elementary problems. Second method of solving limits is factorization. Now in such problems, we'll have this limit x tends to a fx and gx, and more often than not, it will be of the form 0 upon 0, which is an indeterminate form. Now this fx, it can be expressed as some qx into rx, and this gx, it can be expressed as qx into hx, where q is equal to 0. So in this case, this qa is the factor which is making both of them 0. Now if we express this as this limit x tends to a qx rx upon qx hx, this qx and qx, this common factor which is making it of the form 0 upon 0 will cancel, and now from direct substitution we'll get this limit as ra upon ha. Now if we take this simple example, which is this limit x tends to 1 x square plus x minus 2 upon x square minus 1. Now first step in any limit is to check its form. Now we put x as 1, this is 1 plus 1 2, 2 minus 2 is 0, and here it is 1 minus 1 0, so this is 0 upon 0 form, and since both of them they are polynomial, that means one is root of both polynomial in the numerator as well as polynomial in the denominator. Now if we factorize this, we can write this as limit x tends to 1. Now this is x plus 2 into x minus 1, and this is x plus 1 into x minus 1. Now we can cancel this x minus 1 with x minus 1, and we can do so because x tends to 1 and x is not 1. At x equal to 1, this function x square plus x minus 2 upon x square minus 1, it is not defined. But in the deleted neighborhood of 1, this function is defined, and therefore we can cancel this x minus 1 with x minus 1. And now if we use direct substitution, this is 3 and this is 2. So value of this limit is 3 by 2. Now third method of solving a limit is rationalization. So there'll be limits where we'll get these functions which are square root, cube roots, or any nth root. And in such questions, one of the methods that we can use is rationalization. Say for example, we have to find this limit. Limit x tends to 0, and this is under root of 1 plus 5x square minus under root of 1 minus 2x square upon x square. Now if we put x as 0, this is 1 minus 1, 0, and here also this is 0, so it is 0 upon 0 form. Now what we'll do is we'll rationalize it. Now if we rationalize it, we'll get this as limit x tends to 0, and this is under root of 1 plus 5x square minus under root of 1 minus 2x square upon x square into under root of 1 plus 5x square plus under root of 1 minus 2x square upon under root of 1 plus 5x square plus under root of 1 minus 2x square. Now this is a plus b into a minus b. So we can write this as this limit x tends to 0. Now under root of 1 plus 5x whole square, so it will be this 1 plus 5x square minus b square, and b square is 1 minus 2x square upon x square, and this is under root of 1 plus 5x square plus under root of 1 minus 2x square. Now here 1 and 1 will cancel, so we can write this as limit x tends to 0, and this is 7x square upon x square into under root of 1 plus 5x square plus under root of 1 minus 2x square. Now this x square and x square will cancel. Now if we use direct substitution, we can write this as 7 by 2. So value of this limit is 7 by 2. Now let us take another example, which is this limit x tends to 1 2x minus 3 into under root x minus 1 upon 2x square plus x minus 3. Now if we put x as 1, 1 minus 1, it is 0, and here this is 3 minus 3, 0, so this is 0 upon 0 form. Now we can write this as this limit x tends to 1 2x minus 3, and here we'll rationalize it, so we write under root x minus 1 into under root x plus 1, and here we can factorize this as 2x square plus 3x minus 2x minus 3, and this is under root of x plus 1. So it will be this limit x tends to 1, and this is 2x minus 3, and this is a plus b into a minus b, so x minus 1, and here this value, it will be x minus 1 into 2x plus 3 into under root x plus 1. Now this x minus 1 will cancel. Now we'll use direct substitution. So in the numerator we'll have minus 1, and this is 5 into 2, 10. So answer to this limit is minus 1 by 10. Now the fourth method to solve limits is one of the very important methods in limits, and which is using standard limits. Now there are certain limits which we are going to use again and again. So what we have done is we have taken those results in limits as standard results. So we are going to use these limits as standard limits or standard results. And the most important of all is this first result, and which is limit x tends to 0 sine x upon x. Now first thing is we'll check its form. So it should be 0 upon 0 form. Now the standard limit, it says if we have this limit x tends to 0 sine x upon x, which is 0 upon 0 form, then value of this limit is 1. We'll prove this limit in a while when we'll study sandwich theorem or squeeze play theorem. So as of now, we are going to just take this as standard result. So wherever we are going to see sine x upon x, which is 0 upon 0 form, we are going to use this standard limit as 1. Say for example, we have this limit x tends to 0 cube root of 1 plus sine x minus cube root of 1 minus sine x whole divided by x. Now first step here again is checking its form. If we put x as 0, this is 1 minus 1 0, and x is 0, so this is 0 upon 0 form. And since we have this cube root, we are going to rationalize it. And how do we rationalize? Cube root of a minus cube root of b, we are going to multiply it with a to the power 2 by 3 plus b to the power 2 by 3 plus a to the power 1 by 3 and b to the power 1 by 3, and we divide it with it. So it will be a to the power 2 by 3 plus b to the power 2 by 3 plus a to the power 1 by 3 and b to the power 1 by 3. Now this is a minus b into a square plus b square plus ab, which is a cube minus b cube, and that is simply a minus b. So in the numerator we'll have a minus b. So we'll write this as this limit x tends to 0, and here it will be a minus b, and a minus b is 1 plus sine x minus 1 minus sine x upon x, and here we have a to the power 2 by 3, so it will be 1 plus sine x to the power 2 by 3 plus 1 minus sine x to the power 2 by 3 and plus 1 plus sine x to the power 1 by 3 into 1 minus sine x to the power 1 by 3. Now here this 1 and 1 will cancel. So we can write this as this limit x tends to 0. Now it is 2 sine x upon x, and here it is 1 plus sine x to the power 2 by 3 plus 1 minus sine x to the power 2 by 3 plus 1 plus sine x to the power 1 by 3 into 1 minus sine x to the power 1 by 3. Now here we see this x tends to 0 and sine x upon x, which is standard limit, and we know that value of the standard limit is 1. So we'll put the standard limit as 1 and we'll use direct substitution in the denominator. So we'll get this limit as 2 into 1, and if we put x as 0, sine x is 0, and if sine x is 0, it will be simply 1 plus 1 plus 1. So value of this limit will be 2 by 3. So whenever we are going to see this limit, a limit x tends to 0 sine x upon x, that is 0 upon 0 form, we'll take this limit as 1. Now this limit, it can be used in a lot more interesting ways. So rather than having this limit in the form limit x tends to 0 sine x upon x, we may have this limit in the form this limit x tends to a sine of fx upon fx. Now, if we have this condition that limit x tends to a fx, it is 0, then basically when x approaches a, fx approaches 0, and if fx approaches 0, this is sine 0 upon 0, which is 0 upon 0 form. Now here also we'll say this limit is equal to 1, and this limit is much more useful in this form. So rather than having x and x, it can be any function fx provided this fx approaches 0 and it becomes 0 upon 0 form. So if I take a very simple example, this limit x tends to 0 sine 2x square upon x square. Now this is not sine x upon x, but here I see 2x square. Now sine 2x square, it is 0 and x square is also 0. So this is 0 upon 0 form. So here we have fx as 2x square. So what we'll do is we'll multiply and divide everything with 2. Now this is sine fx upon fx, and when x tends to 0, fx, it tends to 0. So here it becomes the standard limit sine fx upon fx. So this value will be 1. So answer to this limit will be simply 2. So it is not just x. It will be any fx provided when x approaches a, fx approaches 0. Let us take another example, and this is this limit x tends to infinite x sine 1 upon x. Now first thing that we'll do is we'll check its form. Now when x is infinite, this is infinite into, now sine 1 upon infinite is sine 0 and sine 0 is 0. So this is 0 into infinite form, which is an indeterminate form. Now we can write this limit as this limit x tends to infinite sine 1 by x upon 1 by x. Now when x tends to infinite, 1 by x, it approaches 0. So basically it is 0 upon 0 form. So in this case, this fx is 1 by x. So here also sine 1 by x upon 1 by x, it is standard limit, and this value is 1. Now there are a few things that we need to keep in mind. Say for example, if I say this limit x tends to infinite sine x upon x. Now when we see sine x upon x, just don't jump into conclusion that this limit is 1. No, this limit is 1 if it is 0 upon 0 form. So for any question, first step will always be checking its form. And this question, if we check its form, this is sine infinite upon infinite. Now sine infinite is oscillating value -1 to 1 and upon infinite, and this value is 0. So sine x upon x, it is not always 1. It is 1 if it satisfies all the conditions for standard limit. And second thing is, while solving problems, say for example, we have this limit x tends to 0 sine 6x square minus 2x upon x square plus x. Now if we check its form, it will be sine 0, which is 0, and this is 0 upon 0 form. Now when x tends to 0, 6x square minus 2x, it also approaches 0. So what we can do is, we can write this limit as this limit x tends to 0 sine 6x square minus 2x upon 6x square minus 2x into 6x square minus 2x upon x square plus x. Now this becomes a standard limit whose value is 1, and here we can take x common. So it will be this limit x tends to 0, and this is x 6x minus 2 upon x plus 1. This common factor x will cancel, so this limit will be simply -2. So we can simplify problems using standard limits. So this standard limit x tends to 0, sin x upon x is 1 when it is 0 upon 0 form. We have many more standard limits and you must remember the result for all these standard limits. Now the second standard limit is this limit x tends to 0, 10x upon x. Now this is also 0 upon 0 form, and if it is 0 upon 0 form, then the value of this limit is 1. Third standard limit is limit x tends to 0, 1 minus cos x upon x square. Now this is also 0 upon 0 form, and if we have this form 1 minus cos x upon x square, value of this standard limit is 1 by 2. Fourth one is this limit x tends to 0, sin inverse x upon x. Now sin inverse 0 is 0, x is 0, so this again is 0 upon 0 form. The standard limit is also 1, and we have this limit x tends to 0, tan inverse x upon x, and it is equal to 1 if it is 0 upon 0 form. Sixth standard limit is this limit x tends to 0, a to the power x minus 1 upon x when a is greater than 0, and value of this limit is ln a. Seventh one is this limit x tends to 0, a to the power x minus 1 upon x, and this is 1. This again is 0 upon 0 form. Previous one also is 0 upon 0 form. Then the eighth one we have is this limit x tends to 0, 1 plus x to the power 1 by x, and this is e, and it is 1 to the power infinite form. And ninth one we have is this limit x tends to infinite, 1 plus 1 by x to the power x. This is also e when it is 1 to the power infinite form. 10th standard limit is this limit x tends to 0, log 1 plus x upon x. Now log 1 is 0 and x is 0, so this again is 0 upon 0 form, and this value is 1. And the 11th one that we have is this limit x tends to a, x to the power n minus a to the power n upon x minus a. Now if we put x as a, it is again 0 upon 0 form, and this is equal to n a to the power n minus 1. Now we can use all these standard limits in the same way that we have used this limit x tends to 0 sin x upon x. So we can use the result directly, or we can use this result for fx rather than x. Now we look at some of these limits. This one is this limit x tends to 0, say 2 to the power x minus 1 upon x. Now this is 2 to the power 0, 1. So it is 0 upon 0 form. So it is limit x tends to 0, a to the power x minus 1 upon x, which is simply ln a. So this limit, it is log 2. Or if we have this limit x tends to 2, x cube minus 8 upon x minus 2. Now we can solve it using factorization. So this is x cube plus 2 cube, which is x minus 2, x square plus 4 plus 2x upon x minus 2. This x minus 2 will cancel, and if we use direct substitution, it is 4 plus 4 plus 4, 12. Or we can solve this question directly using standard limit. Now in this case, n is 3 and a is 2. So this is n e to the power n minus 1, which is 3 into 4, and that is 12. So we'll be using these standard limits in wide variety of forms and in different combinations. Say for example, we have this limit x tends to 0 e to the power 2x square minus 1 upon sine 5x square. Now if we put x as 0, this is 0 and sine 0 is also 0. So this is 0 upon 0 form. Now in this, I see two standard limits. One of the standard limit is limit x tends to 0 e to the power x minus 1 upon x, and this is one if it is 0 upon 0 form, and the other standard limit is limit x tends to 0 sine x upon x, which is one when it is 0 upon 0 form. So what I'll do is I'll write this as this limit x tends to 0, and this is e to the power 2x square minus 1, and to complete this standard limit we have fx here, it should be fx here, so we'll multiply and divide everything with 2x square. So we have multiplied and divide everything with 2x square, and for this sine 5x square, to complete this standard limit we'll multiply and divide everything with 5x square. Now in this case, this x square and x square will cancel. This is standard limit e to the power x minus 1 upon x, and this is 0 upon 0 form. So this standard limit is 1, and this is sine x upon x, which again is 0 upon 0 form. So this is 1. So answer to this limit is 2 by 5. Now we take another example. Say this limit x tends to 0 10x minus sine x upon x cube. Now tan 0 is 0, sine 0 is 0, so this is 0, and x cube is 0, so this is 0 upon 0 form. As of now, I do not see any standard limit. Tan x upon x cube will be infinity, minus sine x upon x cube will be infinity. So what I'll do is I'll take tan x common from this. So we'll write limit x tends to 0, and this is tan x, and if we take tan x common, then it will be 1 minus cos x upon x cube, and we are going to write this x cube as x into x square. Now this is standard limit 0 upon 0 form 1, and this is standard limit 0 upon 0 form 1 by 2. So answer to this limit is simply 1 by 2. Now let us take another example, which is this limit x tends to 0 32 upon x to the power 8 into 1 minus cos x square upon 2 minus cos x square upon 4 plus cos x square upon 2 into cos x square upon 4. Now in this we'll take minus cos x square upon 4 common, so it will be this limit x tends to 0 32 upon x to the power 8, and this is 1 minus cos x square upon 2, and we'll take minus cos x square upon 4 common, and it will be 1 minus cos x square upon 2. So we can factorize this as this limit x tends to 0 32 upon x to the power 8, and this is 1 minus cos x square upon 2 into 1 minus cos x square upon 4. Now the first thing is identify its form. Now cos 0 is 1, 1 minus 1 is 0 upon x to the power 8 will be 0. So this is 0 upon 0 form, and if we look at this, we see there is a standard limit, and which is limit x tends to 0 1 minus cos x upon x square. Now here, rather than having x, we have fx, and this fx is x square upon 2. So we should have fx square. So what we'll do is we'll multiply and divide everything with x square by 2 whole square, and here we'll multiply and divide with x square upon 4 whole square. Now this is standard limit 1 by 2. This is also standard limit 1 by 2. So we are going to write this as this limit x tends to 0, 32 upon x to the power 8 into 1 by 2 into 1 by 2, and here it is x to the power 4 upon 4, and here it is x to the power 4 upon 16. Now x to the power 8 will cancel with x to the power 8, and here this 32 will also cancel. So value of this limit is simply 1 by 8. Now here the question is, if alpha and beta are the roots of this quadratic equation, then solve this limit. Now this is limit x tends to alpha and 1 minus cos ax square plus bx plus c upon x minus alpha whole square. Now if we put x as alpha, it will be this cos 0 is 1, so this is 0 upon 0 form. So we'll convert it in standard limit. So we can write limit x tends to alpha, and this is 1 minus cos ax square plus bx plus c upon, so this is 1 minus cos x upon x square. So it will be this ax square plus bx plus c whole square into this ax square plus bx plus c whole square divided by x minus alpha square. Now this standard limit, it is 1 by 2. So we can write this as limit x tends to alpha 1 by 2, and we can write this quadratic equation as a x minus alpha into x minus beta whole square upon x minus alpha square. Now x minus alpha square will cancel, so answer to this limit will be 1 by 2 a square into alpha minus beta whole square, and that's your option C. Now here the question is, find this limit, which is limit x tends to 3 pi by 4 1 plus cube root of 10x upon 1 minus 2 cos square x. Now what we'll do is, we'll rationalize it using (10x to the power 2 by 3 minus 10x to the power 1 by 3 plus 1, and here also it will be 10x to the power 2 by 3 minus 10x to the power 1 by 3 plus 1. So we write this as, this is limit x tends to 3 pi by 4, and here will be 1 plus 10x, and this is 1 minus 2 cos square x, which is minus cos 2x, and we know that minus cos 2x is 1 minus 10 square x upon 1 plus 10 square x, and here it will be 1 upon 10x to the power 2 by 3 minus 10x to the power 1 by 3 plus 1. Now 1 plus 10x will cancel, so we can write this as limit x tends to 3 pi by 4 1 plus 10 square x, and this is minus, and here will be 1 minus 10x, and then 10x to the power 2 by 3 minus 10x to the power 1 by 3 plus 1. Now if we put x as 3 pi by 4, we'll get this as 1 plus minus 1 square, and here will be 1 minus minus 1 2, and this will be 6. So value of this limit will be simply minus 1 by 3. Now in this question we given this f and theta, and it is given as this product r varies from 1 to n 1 minus tan square theta upon 2 to the power r. Now what we'll do is, we'll multiply and divide it with 2 tan theta upon 2 to the power r. So it will be this product r varies from 1 to n. Now this is tan 2 theta. So it will be this 1 upon 10 to theta to the power r, and this is 2 10 theta to the power r, which is this product r varies from 1 to n, 2 into 10 theta upon 2 to the power r upon 10 theta upon 2 to the power of r minus 1. Now we'll expand this product. Now we put r from 1 to n, it will be 2 into 2 into 2, n times. So that will be simply 2 to the power n. Now here if we put r as 1, it will be this 10 theta by 2 upon 10 theta. Now for r equals to, it will be 10 theta upon 2 square upon 10 theta upon 2, and we'll continue up to 10 theta upon 2 to the power n upon 10 theta and 2 to the power of n minus 1. Now terms cancel only after first one. So all these they will cancel. So we'll get this fn theta as 2 to the power n 10 theta upon 2 to the power n by 10 theta. Now we need to find this limit n tends to infinite fn theta. So this limit n tends to infinite fn theta will be this limit n tends to infinite, and we'll rearrange all this a bit. So we'll like this as 1 upon 10 theta. This is nothing to do with n, and it'll be this 10 theta upon 2 to the power n, and we'll take this 2 to the power n in the denominator, so it'll be 1 upon 2 to the power n. We'll multiply and divide everything with theta. Now when n tends to infinite, 1 upon 2 to the power n tends to 0. So this is 0 upon 0 form. So 10 0 upon 0 is 1. So answer to this limit is simply theta upon 10 theta. Now here the question is, this limit x tends to 0, a to the power 10x minus a to the power sin x upon 10x minus sin x when a is greater than 0. Now we'll take a to the power sin x common, so we can write limit x tends to 0, and it will be this a to the power sin x, and here we get a to the power 10x minus sin x minus 1 upon 10x minus sin x. Now a to the power 0, it is 1, and then this is 10x minus sin x, which is 0. So this is a to the power 0 minus 1 upon 0, which is standard limit ln a. So answer to this question is simply ln a. Now here the question is, we are given that this limit x tends to 0 sin nx into this a minus n into nx minus 10x upon x square, it is equal to 0 for n greater than 0. Now we can write this as limit x tends to 0, and this is sin nx upon x, and here we'll take one of the x with this, so it will be this a minus n into n minus 10x upon x, and it should be equal to 0. Here we'll multiply and divide with n. Now this is standard limit 1, 10x upon x is also standard limit 1, so it will be this n into a minus n into n minus 1 equals 0. So from here we can write a minus n equals 1 by n, or the value of a must be n plus 1 upon n, and that's your option C. Now here the question is, find the minimum value of the expression fx equals ax square plus bx plus c, whose zeros are beta and beta plus 2, which can be obtained by the relation beta equals greatest near function of 2 alpha minus 1, where alpha is given by this limit x tends to 0, 1 minus cos 1 x upon x to the power 4. Now this is 0 upon 0 form. Now we have this standard limit 1 minus cos x upon x square if x is 0. Now if we put x as 0, 1 minus cos x is 0. So we can write this as limit x tends to 0 1 minus cos x upon 1 minus cos x whole square, and into, we can write this as 1 minus cos x upon x square whole square. Now this is standard limit. This is 1 by 2, and this is also standard limit, which is also 1 by 2. So value of alpha is 1 by 8. Now we are given that beta is greatest in the function of 2 alpha minus 1. So value of beta is nothing but minus 1. Now the two roots of this equation are beta and beta plus 2, which is 1. So this equation fx will be x plus 1 into x minus 1, which is x square minus 1. Now if we look at this function, its minimum value will be when the value of x is 0. So this fx, its minimum value will be minus 1 when the value of x is 0. So its minimum value is minus 1, and that is the answer to this question. And actually in this question it should have been this a into x plus 1 into x minus 1, or it will be this a x square minus 1, then it will be this minus a. With minus a, this question doesn't make sense, so we are going along with this minus 1. Now here the question is, we are given this function fn x, which is 10x by 2 into 1 plus secant x into 1 plus secant 2x up to 1 plus secant 2 to the power nx. Now what we'll do is, we'll write this 1 plus secant x as 1 plus cos x upon cos x, and everything else will remain the same. So it is 1 plus secant 2x up to 1 plus secant 2 to the power nx. Now we'll change it in terms of sine and cos. So it will be sine x by 2 upon cos x by 2, and 1 plus cos x will be 2 cos square x by 2 upon cos x, and this is 1 plus secant 2x up to 1 plus secant 2 to the power nx. Now here cos x by 2 will cancel. Now 2 sin x by 2 cos x by 2 is sin x, so we'll get this as 10x into 1 plus secant 2x 1 plus secant 4x up to 1 plus secant 2 to the power nx. Now here it was x by 2 and x, and here it is x and 2x. So situation is same. It is going to be 10 2x and then 1 plus secant 4x 1 plus secant 2 to the power nx. Again situation is same, so it will be 10 2 square x, and it will continue till the end, where it is going to be 10 2n x. So this fn x is 10 2 to the power n into x. Now we need to find this limit. X tends to 0, fn x upon 2x. So it will be this limit x tends to 0. Now fn x is 10 to the power nx, and here it is 2x. Now what we'll do is we'll multiply and divide it with 2 to the power of n minus 1. Now this becomes standard limit, which is 1. So answer to this limit is 2 to the power of n minus 1, and that's your option C. Now here the question is, we need to find the value of this limit x tends to pi by 4 1 plus greatest integer function of x to the power 1 upon log 10x. Now in this case we must know that when x approaches pi by 4, greatest function of x, it is 0. Now this greatest integer function, it takes exact value. It cannot take limiting value. So this form, it is not of the form 1 to the power infinite. So this limit is just going to be 1,
And that's your option B. Now here the question is, find this limit x tends to alpha positive, that is minimum of sin x and fraction part of x upon x minus 1, where alpha is the root of the equation. Sin x plus 1 equals x, where these are greatest integer and fraction part functions respectively. Now if we draw the graph of sin x and fraction part of x, that's the graph of sin x. Now this is 0, this is 1, 2 and 3. Between 0 to 1, this is x. Then we'll have one solution here. Then we'll have one more solution here and one more here. Whichever solution we take, if this is alpha, then in the neighborhood of alpha positive, fraction part of x will always be greater than sin x. So that means this minimum of sin x and fraction part of x will always be sin x. So we're going to write this limit as limit x tends to alpha positive, greatest mere function of sin x upon x minus 1. Now we know that at this point it is sin x plus 1 equals x. Now beyond that we know that fractional part of x will be greater than sin x and fractional part of x is x minus 1. So x minus 1 will be greater than sin x. So we can write sin x upon x minus 1 will be less than 1. And if it is less than 1, then its greatest mere function value will be 0. So value of this limit is 0, and that is the answer to this question. Now here the question is, we need to solve this limit, which is limit x tends to 0 and then this summation greatest mere function of r square sin inverse rx upon x, where r varies from 1 to n. Now we know that when x tends to 0 positive, sin inverse rx, it is greater than rx. So basically sin inverse rx upon rx will be greater than 1, and if we multiply r cube, then we can write r cube sin inverse rx upon rx will be greater than r cube. So this value, it is r cube plus h. So greater function of r square sin inverse rx upon x, it is equal to this summation r varies from 1 to n r cube, and it is equal to 100. Now this is n plus 1 upon 2 whole square, and this is 100. So we can write n plus 1 will be equal to 20, which is 5 into 4. That means value of n is equal to 4. So n is 4, and that is answer to this question. Now the question is, find the possible value of k for which this limit is equal to 1 by 2. Now what we'll do is we'll divide everything with x cube. So we can write limit x tends to infinite 2 minus tan inverse x upon x whole cube, and here it will be 8 upon pi cot inverse mod kx plus k square. Now will be sine 1 by x cube, and here we have x cube, which we are going to write as 1 by x cube, and here it is minus 3k, and it is equal to 1 by 2. Now we'll take this limit x tends to infinite. Now this is 2 minus. Now tan inverse infinite is pi by 2 and pi by 2 upon infinite is 0. Here this is cot inverse infinite. Now cot inverse infinite is 0. So this is 0. Here sin x upon x, when 1 upon x cube tends to 0, it is 1. So it will be this k square minus 3k, that is equal to 1 by 2. So from here we can write k square minus 3k minus 4 equals 0. So it will be this k minus 4 into k plus 1 equals 0. So value of k is either minus 1 or value of k is 4. That means the possible values are minus 1 and 4. Options B and D. Now we have this case when we have assumed that this k is unequal to 0, because this expression cot inverse kx will make a difference whether k is 0 or non-zero. So we have to consider one more case, considering k equals 0. Now if k is 0, we'll have cot inverse 0 and cot inverse 0 will be pi by 2. In that case, we'll have this limit x tends to infinite 2 minus 0. Now this is 8 upon pi into pi by 2. There will be 4 plus k square minus 3k, and if k is 0, this value is again going to be 1 by 2. So that means one more value of k is possible. So there are 3 values possible for k, which are 0, minus 1 and plus 4. Now here the question is, we need to solve this limit x tends to 0 greatest in function of minimum of y square minus 4y plus 11 into sine x upon x, where this box represents greatest in function. Now if we look at y square minus 4y plus 11, we can write this as y minus 2 whole square plus 7. That means it is always greater than or equal to 7. So minimum value of this expression will be simply 7. So we need to find this limit x tends to 0 and then minimum value of 7 sin x upon x. Now we know that sin x is less than x, then sin x upon x, it is less than 1, or 7 sin x upon x, it is less than 7, and therefore its greatest real function will be 6, and that's your option 2. Now the question is, find the sum of an infinite GP whose first term is this limit, whose first term is this limit x tends to 0, tan x minus sin x upon sin cube x. Now if we take tan x common, we can write this as limit x tends to 0, tan x into 1 minus cos x upon sin cube x. Now if we multiply and divide it with x cube, we can write this as limit x tends to 0, tan x upon x, 1 minus cos x upon x square, and then it will be this x cube upon sin cube x. Now this is 1, this is 1 by 2, and this is 1. That means the first term of this geometric series is 1 by 2. So value of a is 1 by 2. Now we need to find the value of its common ratio, which is r. Now r is this limit, which is limit x tends to 1, 1 minus under root x upon cos inverse x whole square. Now here we use substitution. We let x as cos theta. Now if we take x as cos theta, then we can write this as this limit x tends to 1, 1 minus under root of cos theta upon cos inverse of cos theta is theta. So it will be this theta square. We'll write this as limit x tends to 1, and if we rationalize, we will write 1 minus cos theta upon theta square into under root of 1 plus cos theta. Now this is 1 by 2 and it is also 2. So value of r is 1 by 4. So once we have A and R, we can find sum of this infinite GP. Sum of this infinite GP will be A upon 1 minus R. Value of A is 1 by 2 and value of R is 1 by 4. So this value will be simply 2 by 3, and that is the answer to this question. Now here the question is, we need to find the value of this limit. Now this is limit x tends to pi by 2, that is 4 root 2 sine 3x plus sine x whole divided by 2 sine 2x into sine 3x by 2. And what we'll do is we'll take these two together. So we'll write this as cos 5x by 2 minus cos 3x by 2, and then minus, we'll take root 2 common, and it will be 1 plus cos 2x. Now we'll use trigonometric formulas. So we'll write this as limit x tends to pi by 2. Now this is 4 root 2. Now sin c plus sin d is 2 sin c plus d by 2. So it will be 2 sin 2x into cos c minus d by 2. So it will be into cos x. In the denominator, we have this 2 sin 2x into sin 3x by 2. Now this is cos c minus cos d. So it will be 2 sin c plus d by 2, and there will be 8x upon 4. So it will be this sin 2x and then sin d minus c by 2. So there will be sin x by 2 with a minus sign, and here will be this root 2, and this is 2 cos square x. Now here what we'll do is we'll take 2 sin 2x common. So we'll write this as limit x tends to pi by 2, and this is 8 root 2 sin 2x into cos x. And here if we take 2 sin 2x common, we are left with sin 3x by 2 minus sin x by 2. Now sin c minus sin d is 2 sin c minus d by 2, which is sin x by 2 into cos c plus d by 2, which is cos x minus 2 root 2 cos square x. Now since limit is x tends to pi by 2, we have problem with cos x. So what we'll do is we'll write sin 2x as 2 sin x into cos x. So now we'll write this limit as this limit x tends to pi by 2, and this is 16 root 2 sin x into cos square x, and here it will be 8 sin x into sin x by 2 into cos square x minus 2 root 2 cos square x. Now cos square x will cancel. If we put this limit, we'll get this as 16 root 2 upon, now this is 8 and sin pi by 2, and sin pi by 2 is 1 and sin pi 4 is 1 by root 2 minus 2 root 2. So it is 16 root 2 upon 2 root 2, which is 8. So answer to this question is 8. Now here the question is, we need to find this limit x tends to minus infinite, and this is 3x to the power 4 plus 2x square sine 1 by x plus mod of x cube plus 5 upon mod x cube plus mod of x square plus mod of x plus 1. Now since x is minus infinite, that means x is less than 0, and when x is less than 0, then mod of x is simply minus x. So we write this as limit x tends to minus infinite, and this is 3x to the power 4 plus 2x square sine 1 by x minus x cube plus 5 upon minus x cube plus x square minus x plus 1. Now we'll divide everything with x cube. So we can write this as limit x tends to minus infinite, and here will be 3x plus 2 upon x sine 1 by x minus 1 plus 5 upon x cube, and here will be minus 1 plus 1 upon x minus 1 upon x square plus 1 upon x cube. Now everything is sorted other than this x. So we'll multiply it with sine 1 by x. We can write this as limit x tends to minus infinite 3 into. Now we'll write this as sine 1 by x into x, and which can also be written as 1 by x and plus 2 by x sine 1 by x minus 1 plus 5 upon x cube divided by minus 1 plus 1 by x minus 1 upon x square plus 1 upon x cube. Now when x tends to infinite, sin x is 0, so it is 0.04. So this limit, it is 1, it will be 0. This is minus 1, this is 0, all of them they will be 0. So this limit will be 3 minus 1 upon minus 1, which is minus 2. So answer to this limit is minus 2. Now the question is, let m and n be two positive integers greater than 1, and if this limit alpha tends to 0, e to the power cos alpha to the power n minus e upon alpha to the power m is minus e by 2, then we need to find the value of m by n. Now what we'll do is we'll take this e common, so we'll write this as limit alpha tends to 0, and it'll be this e and then e to the power cos alpha to the power n minus 1 upon alpha to the power n. So we can write this using standard limits as limit alpha tends to 0 e into, and this is e to the power cos alpha to the power n minus 1 upon cos alpha to the power n minus 1 into cos alpha to the power n minus 1 upon alpha to the power n, and this value is equal to minus e by 2. Now this is standard limit, and value of this standard limit is 1. So we write this as limit alpha tends to 0 e, and we know that if we take this minus common, we can write this as 1 minus cos alpha to the power n, and if we divide and multiply it with alpha to the power 2n, then this also becomes standard limit whose value is 1 by 2. So we'll put 1 by 2 here. Now 2 will cancel, minus e will also cancel. So from here we'll get this condition that value of m must be equal to 2n. So value of m by n must be 2, and that is the answer to this question. Now here the question is, we need to find the value of this limit, which is limit n tends to infinite cos x by 2 into cos x by 2 square up to cos x by 2 to the power n. Now what we'll do is we'll multiply and divide everything with 2 to the power n sine x upon 2 to the power n. So it will be this 2 to the power n sine x upon 2 to the power n. Now if we take 2 sine x upon 2 to the power n into cos x upon 2 to the power n, this is 2 sin theta cos theta, which is sine x upon 2 to the power n minus 1. So what will happen is we'll keep getting this formula for sine 2x which in the end will be 2 cos x by 2 and sin x by 2, which is nothing but, which is limit n tends to infinity sin x upon 2 to the power n sin x upon 2 to the power n. Now this is n tends to infinite, so 2 to the power infinite is infinite, so this is infinity into 0 form. So what we'll do is we'll write it in standard limit, so it'll be this limit n tends to infinite, and this is sin x, and we'll write this as sin x upon 2 to the power n divided by 1 upon 2 to the power n. Now we'll multiply and divide it with x. Now this is sin 0 upon 0, which is indeterminate form, whose limit is 1. So answer to this limit is simply sin x upon x, and that's your option B. Now the question is, we need to solve this limit x tends to 0 greatest in a function of 1 minus e to the power x sin x upon mod x. Now since this question has both greatest integer and mod with change definition at 0, we have to use left hand limit and right hand limit. So first we'll write its left hand limit. So its left hand limit will be limit x tends to 0 negative 1 minus e to the power x sin x upon mod x. Now we let x as 0 minus h, so it will be this limit h tends to 0 positive, and it will be 1 minus e to the power minus h, and here it will be this sin minus h upon mod of minus h, which we can write as get a function of 1 minus e to the power minus h into minus sin h upon h. Now we know that if h tends to 0 positive, then e to the power minus h, it lies between 0 and 1. Then 1 minus e to the power minus h will be greater than 0 but less than 1. In the same way, we know that if h is positive, then h is nearly 0, then sin h is less than h, and it will be greater than 0, or we can say sin h upon h will lie between 0 and 1. And we multiply it with minus, then we can write value of sin h upon h will lie between minus 1 and 0. So one of them is positive and one of them is negative. So their product negative, and both of them, the value lie between 0 and 1. So value of this product 1 minus e to the power minus h into sin h upon h will lie between minus 1 and 0. And if this value lies between minus 1 and 0, then its greatest in a function will be minus 1. So its left hand limit is minus 1. Now we'll come to its right hand limit. Now for its right hand limit, we'll write limit h tends to 0 positive, and then it will be greater function of 1 minus e to the power h, and here it will be this sin h upon h. Now in this case, e to the power h will be greater than 1. So 1 minus e to the power h will lie between minus 1 and 0, whereas sin h upon h will lie between 0 and 1. Now again this product 1 minus e to the power h into sin h upon h, it will lie between minus 1 and 0. So value of this greatest function again is minus 1. Now since left hand limit is minus 1 and right hand limit is minus 1, Value of this limit is -1, and that's your option A. Now here the question is, find this limit theta tends to 0 greater is a function of n sin theta upon theta and plus n tan theta upon theta. Now we know that sin theta is less than theta is less than tan theta when theta tends to 0 positive. Or we can write when theta tends to 0, sin theta upon theta is less than 1 and it is less than tan theta upon theta. So basically sin theta upon theta, it is nearly 1 minus h, when tan theta upon theta is nearly 1 plus h dash. Now we multiply it with n, then we can write n sin theta upon theta, it will be n minus nh, and in the same way n tan theta upon theta will be n plus n into h dash. Now we take its greater function of n sin theta upon theta. Now this is n minus some small value, so it will be n negative, which is n minus 1, and greater function of n tan theta upon theta. This is n plus small h, which is n. Now we add them. This limit theta tends to 0, n sin theta upon theta plus n tan theta upon theta, it will be n minus 1 plus n, which is 2n minus 1. So answer to this limit is 2n minus 1, and that's your option C. Now this is a very conceptual question. It says if limit x tends to a fx into gx exists for any function f, then which of the following is true? Now clearly answer has to be both these limits fx and gx, they may not exist. And if we take very simple example, suppose this is another limit is limit x tends to 0 mod x upon x, and we know that this limit does not exist as this value is -1 and +1. And suppose the other limit is limit x tends to 0 x upon mod x, which again does not exist, again which is -1 and +1, but if we multiply them, then it becomes a constant function for which this limit is going to exist. So if this fx into gx limit exists, both of them may not even exist, and that's your option D. Now in the questions we are given that f dash x equals 2 minus fx upon x for all x belongs to 0 to infinite, and f1 is unequal to 1, then which of the following is correct? Now we can write this as f dash x plus fx upon x, and it is equal to 2. Now this is dy by dx plus y by x equals to, which is linear equation in y. So in this we'll calculate this integrating factor, which is e to the power integral of 1 upon x dx, and which is e to the power log x, which is nothing but x. Now we'll write answer to this differential equation. So it will be this y into integrating factor, and it will be this integral 2x dx. So we can write x into y will be equal to x square plus c, or y equals x plus c upon x. Now if we put x as 1 and y as 1, we'll get value of c as 0, but it is given that when x is 1, y is unequal to 1, so it clearly means value of c is unequal to 0. So we have this value c unequal to 0. So now we have our function fx. So this fx is x plus c by x, and if we find f dash x will be 1 minus c upon x square. Now f dash 1 by x will be 1 minus c x square. Now if we take this limit x tends to 0, value of this limit will be 1. That means this option A, it is correct. Now, if you look at this option B, which is limit x tends to 0 positive x, and f1 by x will be 1 by x plus cx. Now this is 1 plus cx square, which also is 1, but it is given as 2, so this option B will be incorrect. Now this third one is x square into f dash x. That will be this limit x tends to 0 x square, and f dash x is 1 minus c upon x square. So it will be this x square minus c. So well, this limit is minus c, and since c is unequal to 0, it can never be equal to 0. That means option C is also incorrect. Now if we look at this option D, then we know that mod of fx is x plus c upon x. Now we know that x plus c upon x by 2 will always be greater than or equal to its geometric mean, which is under root c, or we can write x plus c upon x will always be greater than or equal to 2 root c. Now depending on value of c, this expression on the left hand side can take any value. That means this option D is also incorrect. So the only correct option is this option A. Now here the question is, we need to find this limit n tends to infinite, and then it will be this 2 upon pi n plus 1 cos inverse 1 by n minus n. Now what we'll do is we'll take these terms of n together, then we can write this as limit n tends to infinite, and this is n, and it will be 2 upon pi cos inverse 1 by n minus 1 plus 2 upon pi cos inverse minus 1 by n. Now here we'll take 2 upon pi also common, so we can write this as limit n tends to infinite, and here will be 2n upon pi, and this is cos inverse 1 by n minus pi by 2, and this is 2 upon pi cos inverse 1 by n. Now pi by 2 minus cos inverse n is sin inverse 1 by n, so we can write this as limit n tends to infinite and minus sin inverse 1 by n, and this is 2 upon pi, and we'll take this n in the denominator, so it will be 1 by n plus 2 upon pi cos inverse 1 by n. Now as n tends to infinite, 1 upon n tends to 0, so this is sin inverse 0 upon 0, which is standard limit 1, so it will be this minus 2 upon pi, and here it will be this cos inverse 0, and cos inverse 0 is pi by 2, so it will be 2 upon pi into pi by 2. So answer to this limit will be minus 2 upon pi plus 1. Now here the question is, we are given this function fx, and we need to find its left hand and right hand limit at x equals 1. Now if we look at left hand limit, it will be this limit x tends to 1 negative, and this is 1 minus x into 1 plus mod of 1 minus x upon mod of 1 minus x into cos 1 upon 1 minus x for all x unequal to 1. Now when x is less than 1, then mod of 1 minus x will be simply 1 minus x. So we write this as this limit x tends to 1 negative 1 minus x into 2 minus x upon 1 minus x into cos 1 upon 1 minus x. Now this is limit x tends to 1 negative, and here will be this x square minus 2x plus 1 upon 1 minus x cos 1 upon 1 minus x. Now this is 1 minus x whole square, which will cancel with 1 minus x, so will be this limit x tends to 1 negative 1 minus x into cos 1 upon 1 minus x. Now we'll check it forms before solving it. Now this is 0 into, and this is cos infinite, and cos infinite is oscillating value from -1 to 1. Now 0 into anything finite is 0. So answer to this left hand limit is 0. That means this option A it is correct. And option B will be incorrect. Now we'll find its right hand limit. Now for right hand limit will be this limit x tends to 1 positive. Now if x is greater than 1, then 1 minus x mod will be simply x minus 1. So we'll get 1 minus x into 1 plus x minus 1 upon, and this is cos 1 upon 1 minus x. Now here 1 and 1 will cancel. Now this is 1 minus x square, so we can write this as this limit x tends to 1 minus 1 plus x into cos 1 upon 1 minus x, which is minus 2 into cos infinite, which is oscillating value from -2 to +2. And since this value is oscillating, so this limit does not exist. So this right hand limit does not exist. So the correct options are A and D. Now here the questions. ABC is an isosceles triangle inscribed in the circle of radius r. So we have this circle of radius r, and then we have an isosceles triangle inscribed in it. So this is A, B, C, with AB equals AC. If h is the altitude from A to BC, so this altitude from A to BC, it is of the length h, and P is the perimeter of ABC. Now we need to find this limit h tends to 0, delta upon PQ, where delta is area of this triangle. Now radius of this circle is r. So this is r. This is also r. And this side will be h minus r. So this is h minus r. Now from this we can write BD, and BD will be under root of r square minus h minus r whole square. So it will be this under root of 2hr minus h square. Now once we have BD, we can write AB using Pythagoras theorem. This AB square will be AD square, which is h square, plus BD square, which is 2hr minus h square. So length of AB, it will be under root of 2hr. Now once we have all this, we can write perimeter of this triangle. So its perimeter will be 2 times AB, which is root 2hr, plus 2 times BD, which is 2 times under root of 2hr minus h square. Now we will also write area of this triangle. Now area of this triangle will be simply 1 by 2 h into 2 times BD. So it will be 2 times under root of 2hr minus h square. Now this 2 and 2 will cancel. Now we need to find this limit h tends to 0, delta upon PQ. So it will be this limit h tends to 0, delta upon PQ. So it will be this limit h tends to 0. Now delta is h into 2hr minus h square upon, and PQ will be 2 root 2hr plus 2 into 2hr minus h square whole cube. Now in the numerator, we'll take this h common from the root, so it will be this limit h tends to 0, and then it will be this h to the power 3 by 2 under root of 2r minus h, and here we'll take under root h common, so it will be h to the power 3 by 2, and we are left with 2 root 2r plus 2 into root 2r minus h whole cube. Now this will cancel. If we put this limit h tends to 0, we'll get this as under root 2r upon, now this is 2 root 2r plus 2 root 2r. So it will be 4 root 2r and 4 root 2r cube will be 64 into 2 root 2 r root r. Now root 2r will cancel. So this value will be 1 by 128r. And that's your option C. Now here the question is, we need to find this limit x tends to pi by 2 sin x upon cos inverse greatest linear function of 1 by 4 into 3 sin x minus sin 3x, where this box represents greatest linear function. Now if we look at this 1 by 4, 3 sin x, now minus sin 3x is 3 sin x minus 4 sin cube x. Now this 3 sin x will cancel, this 4 will also cancel, so this value will be simply sin cube x. So we can write this limit as limit x tends to pi by 2 sin x upon cos inverse greatest linear function of sin cube x. Now when x tends to pi by 2, sin cube x tends to 1, but it is still less than 1 because it will be 1 only at pi by 2. So within the vicinity of pi by 2, it will be less than 1. So this sin cube x, it is nearly 1 but less than 1. In that case, greatest linear function of sin cube x will be nothing but 0. So it will be this sin pi by 2 1 and then cos inverse 0, and cos inverse 0 is pi by 2. So answer to this limit will be 2 upon pi, and that's your option A. Now here the question is, this limit x tends to infinite cot inverse under root of x plus 1 minus under root x, and it will be this secant inverse 2x plus 1 upon x minus 1 whole to the power x. Now we write this as limit x tends to infinite. When we rationalize this, we can write this as cot inverse, and it will be 1 upon x plus 1 plus under root x, and this one is secant inverse 2 plus 3 upon x minus 1 to the power x. Now this is cot inverse 0, and here it will be this secant inverse 2 to the power infinite. Now cot inverse 0 is pi by 2, and secant inverse infinite is also pi by 2. So value of this limit is 1, and that's your option A. Now here the question is, we are given this limit x tends to 0 sin x minus 10x whole square minus 1 minus cos 2x to the power 4 plus x to the power 5 7 tan inverse x to the power 7 plus sin inverse x to the power 6 plus 3 sin to the power 5x. Now here we'll take tan x common, so we can write this as limit x tends to 0 tan x whole square, and then will be cos x minus 1 whole square, and we can write this as 2 sin square x whole to the power 4 plus x to the power 5 upon 7 tan inverse x to the power 7 plus sin inverse x to the power 6 plus 3 sin to the power 5x. Now what we'll do is we'll divide everything with x to the power 5. So we can write this as limit x tends to 0. Now it will be this 10x whole square upon x, and we'll write this as 1 minus cos x upon x square whole square, and here will be 2 to the power 4 sin to the power 8x upon x to the power 5 plus 1. This is 7 tan inverse x to the power 7 upon x to the power 5 plus sin inverse 6 upon x to the power 5 plus 3 sin to the power 5x upon x to the power 5. Now here this is 1 by 2 square, 10x upon x is 1, and then we have this additional 10x which will be 0. So this part is 0. Here also sin to the power 8x upon x to the power 5 will be 0. Tan inverse x to the power 7 upon x to the power 5 will be 0. Sin inverse x to the power 6 upon x to the power 5 will be 0. And sin x upon x to the power 5, it is 1. So answer to this limit will be simply 1 by 3, and that's your option C. Now the question is, let Sn be the sum of this series sin x plus sin 2x plus sin nx. Now basically angles are in AP with common difference of x. So what we'll do is we'll multiply and divide it with 2 sin x by 2. So it'll be this 2 sin x by 2 and then sin x plus sin 2x up to sin nx. Now we like this is 1 upon 2 sin x by 2, and will be 2 sin x by 2 into sin x, 2 sin x by 2 into sin 2x, 2 sin x by 2 into sin nx. Now will be 1 upon 2 sin x by 2. Now this is 2 sin A sin B. So it will be cos A minus B, which is cos x by 2 minus cos 3x by 2. Now here will be cos 3x by 2 minus cos 5x by 2. And in the end we'll have cos n minus 1 by 2x minus cos n plus 1 by 2x. Now all these terms, they'll cancel. So basically we'll get this Sn as 1 by 2 cot x by 2 minus cos n plus 1 by 2x upon sin x by 2. Now if we take this summation, r varies from 1 to n, SR will be this 1 by 2 n cot x by 2, and then minus this summation, r varies from 1 to n cos r plus 1 by 2x upon sin x by 2. Now we need to find this limit n tends to infinite summation SR upon n. Now will be this limit n tends to infinite. Now here n and n will cancel. This 1 by 2 cot x by 2, and then minus this summation r varies from 1 to n cos r plus 1 by 2x upon sine x by 2. And the question it is given that x is unequal to 2k by, that means this cos r plus 1 by 2 is not equal to 1. That means this cos r plus 1 by 2 is less than 1. So this summation, here we'll also have this n. This summation will be less than n, and in the denominator we have n. So value of this limit when n tends to infinite will be 0. So answer to this question will be simply 1 by 2 cot x by 2. Now here the question is, we need to solve this limit, and this limit is, suppose we'll write this limit as L equals limit x tends to a, and then LB this a to the power 1 by 2 plus x to the power 1 by 2 upon a to the power 1 by 4 minus x to the power 1 by 4 to the power minus 1, and then minus 2 ax to the power 1 by 4 upon, and this is x to the power 3 by 4 minus a to the power 1 by 4 x to the power 1 by 2 plus a to the power 1 by 2 x to the power 1 by 4 minus a to the power 3 by 4 whole to the power minus 1, and then minus, this is root 2 to the power log 4a and whole to the power 8. Now first we'll simplify this. Now this is 2 to the power. Now this is 1 by 2 and 2 square is also 1 by 2. So this is 2 to the power log 2 and a to the power 1 by 4. So this expression is nothing but this is a to the power 1 by 4. Now what we'll do is we'll actually let a to the power 1 by 4 as capital A and x to the power 1 by 4 as capital X. And we can write this L as this limit, and here it will be a square plus x square upon a minus x to the power minus 1, and then minus, and this is 2 ax upon x cube minus ax square plus a square x minus a cube whole to the power minus 1, and then minus a whole to the power 8. Now this is this limit, and then if we take this reciprocal, we can write this as a minus x upon a square plus x square, and this is minus 2ax, and if we factorize this, we can factorize this as x minus a into x square plus a square whole to the power minus 1 minus a whole to the power 8. Now we simplify this, we can write this as limit, and then it will be x minus a into x square plus a square, and here it will be minus x minus a square minus 2ax to the power minus 1 minus a whole to the power 8. Now it will be this limit, and then it will be this minus x square plus a square upon x minus a and x square plus a square whole to the power minus 1 minus a to the power 8. Now x square plus a square will cancel, and if we take this reciprocal, then it will be this limit a minus x minus a to the power 8. Now a and a will cancel, So this is limit capital X to the power 8. Now capital X is small x to the power 1 by 4. So it will be this limit x tends to a x to the power 2, and which is a square. So answer to this limit is a square, and that's your option C. Now here the question is, let Px be a polynomial of degree 4 having extremum at 1 and 2, and it says limit x tends to 0, 1 plus px upon x square, it is equal to 2. Now if 1 plus px upon x square is equal to 2, that means minimum power of x in px, it must be x square and its coefficient must be 1. So it will be this x square, then ax cube plus b x to the power 4. Now we find p dash x will be 2x plus 3ax square plus 4b x cube. Now p dash 1 is 0 and p dash 2 is 0. Now if we put p dash 1, we get 3a plus 4b, and there will be minus 2. And if we put this as 2, we'll get this as 6a plus 16b, and there will be minus 2. Now we'll multiply this first with 2 and we'll subtract it. Then it will be 8b, and 8b equals to 2. Value of b is 1 by 4, and if we put b as 1 by 4, it will be this 4. Value of a is minus 1. So this function px, it will be x square minus x cube plus 1 by 4 x to the power 4. Now we need to find the value of p2. Now p2 will be 4 minus 8 and plus 4, which is 0. So answer to this question is simply 0. Pi upon n plus 2 is some constant, say theta. So we'll actually write this as Fn is this summation, k varies from 0 to n sine k plus 1 theta into sine k plus 2 theta whole divided by this summation, k varies from 0 to n sine square k plus 1 theta. Now we'll multiply and divide it with 2. Now this is 2 sine A sine B, and we know that 2 sine A sine B is cos A minus B minus cos A plus B. So it will be this summation, k varies from 0 to n and cos A minus B. So it will be k plus 2 theta minus k plus 1 theta. It will be simply cos theta minus this summation, k varies from 0 to n, and it will be cos A plus B, and there will be 2k plus 3 into theta, and the denominator will be this summation, k varies from 0 to n and 1 minus cos 2 theta. So it will be cos 2 into k plus 1 theta. Now since theta is independent of k, this summation cos theta is summation of constant. So it will be this n plus 1 into cos theta. So we can write Fn as n plus 1 cos theta minus this summation, k varies from 0 to n cos 2k plus 3 theta upon this summation 1 will also be n plus 1 minus this summation, k varies from 0 to n cos 2 into k plus 1 theta. Now first we'll simplify these two summations. Now this first summation is summation k varies from 0 to n cos 2k plus 3 theta. Now if we put k as 0, so it will be this cos 3 theta, cos 5 theta, cos 7 theta up to cos 2n plus 3 theta, where angles are in AP. Now in this case, value of alpha is 3 theta and value of beta is 2 theta. That's your common difference. We know that sum of this series is sine n beta by 2. N beta by 2 will be, number of terms is n plus 1, and beta by 2 is theta, upon sine beta by 2, which is sine theta, into cos alpha plus, which is 3 theta, plus n minus 1, which in this case is n, into beta by 2, which is theta. So it will be this sine n plus 1 theta into cos n plus 3 theta whole divided by sine theta. And if we look at this second series, which is this summation, k varies from 0 to n cos 2k plus 1 theta, will be this cos 2 theta plus cos 4 theta. Now in this case, alpha equals beta equals 2 theta. Number of terms is n plus 1, and again angles are in AP. So we can write this as sine n beta by 2, so it will be this sine n plus 1 theta upon sine theta into cos a plus n minus 1 into theta. So it will be this sine n plus 1 theta into cos n plus 2 theta whole divided by sine theta. So now we have result for both the summations. So we can write this function fn as n plus 1 cos theta minus this sine n plus 1 theta cos n plus 3 theta upon sine theta divided by n plus 1 minus sine n plus 1 theta into cos n plus 2 theta upon sine theta. Now we have taken pi upon n plus 2 as theta, so we can write n plus 1 theta as pi minus theta. So sine n plus 1 theta will be sine theta, and n plus 2 theta will be simply pi. So sine n plus 1 theta and sine theta will cancel, and here we'll get this as n plus 1 cos theta minus cos. Now n plus 2 theta is pi, so it will be this pi plus theta, and here will be this n plus 1 minus cos pi. Now cos pi plus theta is minus cos theta. So here will be this minus minus plus. So we can write this as cos theta into n plus 2 upon n plus 2, and will also cancel. So basically this function fn will be cos pi upon n plus 2. So now we have our function fn, which is cos pi upon n plus 2. Now the first part is f4. Now this f4 is cos pi by 6, and cos pi by 6 is root 3 by 2. That means option A is correct. Now f6 will be cos pi by 8. Alpha is tan of cos inverse f6, and cos inverse x is pi by 8. So it will be this tan pi by 8, and tan pi by 8 is simply root 2 minus 1. Now we take this one on the left hand side in square, we get alpha square plus 1 plus 2 alpha will be equal to 2, or alpha square plus 2 alpha minus 1 equals 0. That means this option B is also correct. Now for this C, we need to find f5. f5 is cos pi by 7. Now sine 7 cos inverse f5 will be sine 7 pi, and sine 7 pi is 0. That means option C is also correct. And then this limit n tends to infinite, fn will be this limit n tends to infinite cos pi upon n plus 2. Now this is cos 0 and cos 0 is 1. So option D is incorrect. So the correct options are A, B and C. Now here the question is, if alpha and beta are two distinct real roots of this equation, ax cubed plus x minus 1 minus a equals 0, where a is unequal to minus 1 or 0, and alpha and beta they are unequal to 1, then we need to find the value of this limit. Limit x tends to 1 by alpha 1 plus ax cubed minus x square minus a upon e to the power 1 minus alpha x minus 1 into x minus 1. Now if we put x equal to 1 in this equation, we'll get a plus 1 minus a equals 0. That means one of the roots of this equation is 1. So roots of this equation are 1, alpha and beta. Now we'll find the equation whose roots are 1 upon alpha and 1 upon beta, and for that we'll replace x with 1 upon x. So it will be this a upon x cube plus 1 upon x minus 1 minus a equals to 0, or we can write this equation as 1 plus ax cube minus x square minus a equals 0. So if we take this limit x tends to 1 by alpha, then 1 plus ax cube minus x square minus a, it will be 0, as 1 upon alpha is one of the root of this equation. So basically now we know that this equation has three roots, 1 upon alpha and 1 upon beta. So we can write this limit L as limit x tends to 1 by alpha, and if we factorize it, we can write this as 1 plus a into x minus 1 upon alpha, x minus 1 upon beta upon e to the power 1 minus alpha x minus 1 into x minus 1. Now this x minus 1 will cancel. We can write this as limit x tends to 1 by alpha. Now it will be this 1 plus a. Here we'll take minus common. So it will be this minus and then 1 minus alpha x, and here will be this beta x minus 1 upon e to the power 1 minus alpha x minus 1 into alpha beta. Now this is standard limit e to the power x minus 1 upon x. So it is 1, and we'll put x as 1 upon alpha. We can write this limit L as minus 1 plus a beta upon alpha minus 1 upon alpha beta, or it is 1 plus a into alpha minus beta upon alpha square beta. So value of this limit is 1 plus a into alpha minus beta upon alpha square beta. Now 1 alpha and beta, they are roots of this equation. So if we find their product, 1 into alpha into beta, it is minus c upon a, which is 1 plus a upon a. So we'll put alpha beta as 1 plus a upon a. So it will be 1 plus a into alpha minus beta upon alpha, and it will be 1 plus a into a. So I'll cancel. So value of this limit, it will be A into alpha minus beta upon alpha. Now we compare it with this given limit, then we can write value of L must be 1, value of K must be 1. Now we need to find the value of K into L. Value of K into L is 1.